Hello ladies and gentlemen, and welcome back to what is essentially going to be the 7th lab for GGS300 Quantitative Methods for Spatial Science. Today we're going to be focusing on implementing those different two-sample tests that we carried out within the lecture. So you'll be very familiar now with the slide set which you should have available, and which hopefully you covered the previous lecture where we went through all those different tests. Today the lab is going to be hopefully a lot shorter. I appreciate there was a lot of content in the previous session, but what we're going to do is we're basically going to run through some of those examples and actually just generate those test statistics and test the significance values for those different types of tests using some very simple examples that we've got either from data sets or from within the book essentially. Okay, so let's get stuck into the detail. I assume you've got your R all set up and that you're able to basically download the code and go through these particular examples in tandem with the video, run the code, understand what's happening. So we're going to cover today in the 7th lab two-sample difference of means tests and also matched pairs difference of means tests. Okay, so the first set is where you have independent data, and the data are either parametric, so normally distributed, or non-parametric, so not normally distributed. And then on the other side, if you have dependent data, so basically you're surveying the same people or the same places twice, so you have matched samples, then you would be looking at using a matched t-test if the data was normally distributed, or looking if the data were not normally distributed. At a non-parametric test, such as the Wilcoxon matched pairs signed ranks test. Okay, so let's get stuck in, and you should have a data set available to you, and that data set essentially is covering data which shows poverty rates by state for the years 2000, 2010, 2012. And the states are also categorized regionally, so into the 4 kind of main, very aggregated geographical regions for the states, so north, east, south, west. And essentially this work is hypothesizing that people who live in the west generally would experience lower poverty rates. So the states in the west would experience lower poverty rates than in the south. Okay, so essentially we have West Coast booming tech industries, and then we have areas in the south where arguably there's far fewer high-value industries, and as a consequence the poverty rates might be larger in those areas. Okay, so what we want to do is test whether that's true. So you should have the data, should just be able to use our kind of standard little nifty one-liner that we have within R now, which just says get me the directory name from the RStudio API and give me that allocated as a folder. So if I run that, press Control Enter, then I get the string of the folder, and then basically I can press Control Enter again on that line. It should set the working directory to being the folder in which we have this R script in. Okay. So that should allow us to access that data, and then we can just go to the read table function, load in the poverty.txt data that we have. So we allocate it into the global memory of this R session. You can look at the poverty data up there and inspect it, or you can print it, for example, to the command line here. We basically have the state, that regional indicator which I mentioned before. So it's a bit more nuanced than the 4 categories I mentioned, so you can take a look at that. And then we also have the poverty rate, so percentage of people in poverty for the year 2000, 2010 and 2012. R does not let you have numbers which start the column headers, so that's why you have this X before the year here. And just before we progress, I was thinking one little nice nifty R trick, which I'm just able to show you very quickly, is if you use the unique function, you can actually work out how many unique values you have in a particular column, as I've shown here. So remember before I was a bit like, I think there's four regions that we're talking about in the States here for our data set. Well, actually you can find that fairly easily if you go unique, and then you give it the data frame and the column which you're interested in, it will just print those unique values out to the command line here, which is really handy. In fact, I use it quite regularly if I have to order something. So like order the levels of a string as this indicates here, which sometimes you may need to do for a graph. So it's basically saying which order you want the categories in. Then basically you need to know how many unique values you have to tell R what to do, and therefore this is a kind of a handy function. Okay, look, let's progress. We've got the data loaded in now. What we're able to do is we're actually able to create two new arrays, and those arrays have the data rates based on the West and the South. So what this is doing is it's saying in the poverty data frame, go to the column which is region and find me all of those rows which have a W for the West, okay? And then it basically says, find me all of the values for the year 2012 for the poverty rates, which are equal to, which have a region equal to W, okay? So when we get this is an array of all of the poverty rates for those regions which equal W, okay? So you can see it just up here. We can do the same for SP poverty, S poverty, so southern poverty, and therefore we can just do a subset based on that S column there, and we get all the poverty rates for 2012 for the southern states. Great, so now we can look at this data, so we can do just a little bit of a summary. So if I enter Control Enter, when we're using the summary, it's going to give us the minimum, the first quartile, the median, the mean, the third quartile, and the maximum. And straight away we can see for the Western poverty, the Western states, compared to the Southern states, the mean rate is only 13.87% for the Western states, and that's compared to 16.9% for the Southern states, so it's quite substantially higher. And the maximum poverty rate is also lower in the Western states compared to 22 over here, only 20.4 in the Western states, and the minimum is also quite substantially different, so lower in the Western states, 9.6 versus 9.9 in the South. So I think that that's fairly straightforward. We can also see a much higher median, which is indicative of the distribution being really quite skewed. Actually, it's negatively skewed, but it's because you've got so many more values which are higher above the mean, which is causing that to happen. So we can show that actually. If we look at the histogram, so for the Western states, it's fairly regular. There's not too much of a difference, but over here, when I say it's negatively skewed, it's because you have this long negative tail and then this large clump of quite high poverty states, unfortunately. Over here, the higher rates are above 16% of people living in poverty, sadly. So look, that's useful, that's good information for us to kind of start. We're now able to state our hypothesis, so a little bit similar to how we did those 6 steps for testing previously. So we know that our null hypothesis is going to basically be where we don't expect any difference between the Western states and the Southern states. And the alternative hypothesis will be essentially that we would expect the Western region to have lower poverty rate than the Southern regions, okay? So we can see that there for the null, where we'd expect the mean poverty rate to be equal to the mean poverty rate for the West and the South, respectively, compared to the alternative poverty rate, where essentially the mean rate would be lower in the West as opposed to the South, okay? So now we can actually test that, so we can get the number of samples in each of our data pools. So for sample 1, which is the West, we have 13 states, and in the South we've got 17 states. We can then get the mean for both of these poverty rates, so 13.87 and 16.9 here. And then we can get the standard deviation as well, so 13.86 and standard deviation 3.27 and 3.22. Sorry, it's been a long day. Okay, great. So hopefully that's given us those values that we need to now be able to carry out the test. So before we do that, let's just go back to the formula that we covered previously so you know what we're doing. We're trying to get these mean values here, and then obviously we need the standard error of the difference of the means as well, which means that down here we need the standard deviation before we square it to get the variance, and we need the number of samples in each sample. Okay. So we know that these values are not over 30, so we're going to do a one-sided two-sample t-test. But generally we're going to use t-test anyway because we don't always know the population parameters for variance. We do want to specify our significance alpha value to a fairly standard level, so normally we want to be 95% confident that our result hasn't just occurred by chance, so as a consequence we have an alpha value of 0.05. So this is going to also relate to the likelihood of a type 1 or a type 2 error occurring. So in this case, if we have a 0.05 significance level, then there's a 5% chance of our result completely occurring due to randomness, but that's an acceptable level of error that we're willing to tolerate. So now we've got the alpha value, what we need to do is get the number of degrees of freedom. So in this case, we've got the sample size for sample 1 and the sample size for sample 2. And because we've got two samples, so we have to subtract 2 this time, so the number of degrees of freedom is always n minus 1. We have 2 samples, so we're adding up the samples for both of them and then subtracting from 2. Okay, so I hope that's not too complicated for you. When we actually do that, we had 30 samples, so we end up with 28 as the number of degrees of freedom, okay, because there were 2 samples. So yeah, we had 30 sample points across 2 samples, just to clarify. Great, so now we can get on to delineating the regions of rejection. So we covered this previously, and what was really nice in those previous labs was we actually created the distribution, and then we coloured in that area of rejection in advance. So it's kind of very clear that if our mean occurred in that particular area, then we would expect it to be significantly different. So we can get our t-critical value. And the t-critical value is using the qt function, so we want the quantile in the t-distribution that relates to our alpha as our t-critical value. So in this case, because we want it in the lower part of the distribution, we're getting minus 1.7 standard deviations below the mean. And obviously we're using one-tailed here, and therefore we're not splitting the alpha value, we're expecting all of that value to occur in one part of the distribution. We then create the t-distribution curve as this x, and then we can plot it. So we've got the number of standard deviations down here, and then we've got the frequency of values up here. And then basically we can plot our critical value area down here. So if our mean is below this critical threshold, then we know that there's a significant difference, and we could be 95% sure that our result just hasn't occurred by chance. Okay, so we're focusing on this poverty example. The question was that the mean poverty rate by state in the Western region is the same as in the alternative hypothesis that we're interested in testing is the mean poverty rate by state in the West region, and that it's lower than in the Southern region. Okay, so when we say it's lower there, that's why we're using this one particular part of the distribution down here. And now what we can do is we can calculate the t-test statistic. Okay, so we had this equation before. We want to get the standard error here. The way for us to do that is to take the square root of this equation. So what we need to do first is we need to get the standard deviation for sample 1. We need to square it to get the variance, and we divide it by the number of samples that we've got in that sample, the number of sample points. Then we have to do the same for the second sample, and we add them together and take the square root, which gives us a standard error of 1.196. Okay, so 1.2 essentially. And then we're able to get the t-statistic here, so we need to get the numerator first. So it's very simple, we just take the mean of that second sample and subtract it from the mean of the first sample. And then what we need to do is then just divide that numerator by the standard error that we've already obtained. And when we do that, we get a t statistic of minus 2.53. Okay, so it's pretty large. We know that, and the t-calc is larger than the magnitude of the t-critical value. So this value, minus 2.53, is larger than the t-critical value of minus 1.7. As a consequence, we are able to reject the null hypothesis at the 95% confidence level. So we're 95% confident that the results haven't just occurred by chance, in which case we actually found evidence that the western region of the United States, so all of those states down the west coast, basically has a lower poverty rate on average compared to the southern regions. So that all of those states in the south, on the southeast border, below the Mason-Dixon line. Okay. Right, so let's move on. Obviously there we calculated it manually. So that was kind of taking all of that information we took in the lecture and then putting it into some sort of sequence of steps for us to get some sensible results. Now let's calculate that using the inbuilt tests that we have within R. But just before we do that, let's first get the p-value for this, this particular size t. So we can use the pt function. We can give it the number of degrees of freedom. We can ask for it to be in the lower part of the distribution. When we do that, we get a p-value of 0.0085, so highly significant, well below the 0.05 level that you'd normally be looking for significance. We are then able to use the built-in test, and the test is able to basically run these t-tests between the Western poverty and the Southern poverty case at the confidence level of 0.95, so with an alpha value of 0.05. And when we do that, we get values that pretty much match what we got before. Okay, so 2.53 up here, and sorry, minus 2.53 up here, and minus 2.53 down here. At the number of degrees of freedom, slightly different the way R calculates it here in built, but pretty much the same, so I'm not worried by that. And the p-value is down here at 0.008, so very similar to what we got before. Okay. Great, so hopefully that's kind of clear to you now how we would do that explicitly, manually, and then also how we would do it when you know how to do the process. You just use the inbuilt function and it does it all for you. You just then need to know how to interpret the results, obviously. Great, so let's move on, and we want to focus now on what happens if you don't have normally distributed data, so a non-parametric test. Imagine that we first need to rank that data. But we have to put all of the values in a single vector. Fine, we can do that fairly easily. So we can tell the class apart. We'll make a vector of the class and then put the class and the values in the data frame. Okay, so this is just data manipulation. So very often they say that you'll spend 5 to 10% of your time doing the actual statistical testing, but then the 90% of your time you're going to be spending doing this stuff. It's actually just data manipulation. It's also called data munging. It just means getting the data in the right shape and doing all the processing before you can then carry out the actual testing. So this is just basically creating a class here for West and for South. It then gets the proportions which we're getting here, and we basically then going to put them together into a data frame called values. So we have the class here and the relevant proportion listed down here on the second column for the South and the West. Okay, so we're now able to rank these. So we've got the proportion. So this is the poverty rate. So the proportion of the population, unfortunately, living in poverty. And then we're also able to rank these. Okay, so all we're doing with ranking is we're sorting the data based on the magnitude of it, and we're just in each row we're just placing a value. So in row 1 we allocate it a rank of 1. In row 2 we allocate it a rank of 2. In row 3 we allocate it a rank of 3, and so on and so forth. Okay. Those ranks have been placed into the global environment, and actually we can just combine it all now into a single data frame. So we have the class for the region, we have the poverty rate as the proportion for the states, and then we have the rank. So if we go to the lowest, here it's got rank 1, The second lowest, it's got rank 2. The third lowest, it's got rank 3, and then we can go all the way up to the highest rank, which understandably, because we have 30 data points, would have 30 as the highest rank of the overall data set. So now what we can do is we can go basically use the same nifty piece of code that we used before. So we're saying go into the combined data frame, and then what I want to do is just subset all of those rows which are equal to the west region. Okay, so this just has the western region proportions and ranks. And then we do the same for the south here. So when you have the comma like this in the square brackets, it's saying subset the rows. Okay, so that's how you're able to subset these rows from this one data frame into this other one that you create called either west or south. Then it's much easier for us with just a single data frame for the west or the south to then just sum those ranks. Okay, so we know if we go to the main, here we go to the main equation, what we want to do is get the sum of the ranks for the sample. That's fine, we can just use the sum inbuilt function here, and we end up with W1 and W2. So we get 145.5 for W1 and 319.5 for W2. Okay, so W is the sum of the ranks of the class. We know that. I've just covered it. And then this, in this next part, what we're doing here is we're basically getting that more complicated value here. So this is the mean ranks of Wi. So you could basically use this equation just here. So it's the sample size for the sample you're using times by, and then it's the sample size for the first sample, the sample size for the second sample, plus 1 as the numerator divided by 2, okay, multiplied. When we do that, and I think that these are all fairly easy now for you to understand because you know these equations, we've covered them before, it's just making sure that you get the right numbers in the right place. And we get 201.5 for this first W1 bar, and for this is the standard error here, so this is this SW, the standard deviation of W, sorry. We need to take the square root of the sample sizes multiplied by this particular set of brackets here, and that's again a fairly simple equation for us to carry out. It looks more intimidating than it actually is. Okay, great. So once you've got all of those constituent components, we can just calculate this equation here. So we want the test statistic ZW, and it's equal to the WI minus the W bar I divided by the SW. Okay, so we're able to do that, and when we do, we get this minus 2.34 just here, so you can see it in the global environment, minus 2.34. And then actually we can query what the p-value is going to be there. So we know that this is already a very low value, and therefore it's highly likely to be significant. But if we use the p-norm, it tells us, well, for this number of standard deviations, this is the probability value that we obtain for that particular place in the distribution. So it's 0.0095461. So it's a really small p-value, and therefore it's indicative of the fact that there is a significant finding. So let's just use the built-in function to check this. Obviously we're going to reject the null hypothesis in this particular case. If we use the built-in function, it gives a W stat, so it gives the Wilcoxon rank stat basically, that we won't worry about. We'll just use the p-value, which should be similar to what we got above. So this is complaining, it's just saying that it can't get an exact p-value because there are ties in the data set. And remember, when you get ranks that are in a similar place, so it's fine, just ignore that. We got sensible results though. We got a p-value which is reasonably close to the value that we got, so it's definitely significant, although it's slightly different. It's been rounded up, and it's also been affected by these ties that we have in the data frame. But the point is, it's indicative of a significant result, and therefore it kind of backs up what we've already been doing before. using the more manual approach. Okay, so let's move on then. It would be nice now to consider matched pairs difference tests. So in the same data set, we have data for poverty by state for different years between 2000 and 2010. And you know that, because I mentioned this before, there was the global financial crisis in 2007, 2008, and this was a horrific time. There was very, very high unemployment, and unfortunately, the poverty rate increased during this time because people became unemployed. We can test if this hypothesized increase that we have here actually took place, and if it's true in the data that we have. So let's save the data that we've got for two different periods first. So we're going into the poverty data set, and we're saying go to the year 2000 and the year 2010, and then just create these into our own vectors just here, our own arrays. So we've got the poverty 00 and the poverty, so poverty 2000 and poverty 2010 data saved. We can then find a summary for these, so we can see that the poverty was around 10.8% in 2000, the turn of the millennium, whereas it was much higher by 2010, 14.26% of people living in poverty, so really sad. The maximum has also increased drastically, and the minimum has sadly also increased. But we can view this on a histogram. So this in the year 2000 is quite normally distributed data. You can see how we've got states down here in the sub 6% poverty line. Most are below 10% poverty. But actually, as we then look at the data for 2010, wow, some of them are really increased. You can see that we don't have that many below 6 anymore. In fact, we don't have any. And you can see that many of those states have increased into the 10, 12, 16, 18, 20, all the way up to 22% up here. So a really quite substantial increase in poverty rates, which obviously is very sad. So we can do a t-test by hand, so we can state the hypotheses. So the null hypothesis would be that there's no difference between the poverty rate between 2000 and 2010, whereas the alternative would be the alternative hypothesis that the poverty rate has increased over this time. So the X bar is much larger in 2010, the mean poverty rate is larger relative to the year 2000 level, okay? So the order matters, make sure it matches the question at hand, yes. We then need to define the test. So we know all the matched pairs tests use t, so let's get the needed stats for both of our variables. Obviously this is a matched pairs test because we have the poverty rate for 2000 and 2010, and we're comparing a dependent sample, so it's the same state in two different samples, so you need to compare back to the original value. We can get the number of samples in each one of these samples, so the number of sample points in each one of these samples, and we get 51 in each one of those. So if we just go to here we go, sorry, N1, we can see 51 in each one of these, that's great. And then we can go to the X bar for mean 1, for sample 1. And we can get the X bar for the second sample. So we just use the inbuilt mean function, which I think by now you guys should all know. You should know this by now. So that's great. So that just gives us an easy way to calculate the average, the arithmetic average. And we've got 14.25% on average for sample 1 and 10.86% on average for sample 2. And we can get the D, so that's the difference between these, by subtracting the, so these are the differences, subtracting the actual data sets that we have for those poverty rates. So remember, when you have two vectors like that, it's going to go to row 1 in the first vector and row 1 in the second vector, and it's going to subtract one from the other based on what we said here. So this just gives us another vector of values with all of the differences. So let me show you where we are with that. So we do the match pairs. We want to get this test statistic here, TMP, so we need to get the mean of the differences, so it's the mean of the matched pairs differences, and we need to get the differences by subtracting the first set of sample values from the second set of sample values. And when we do that, we get this D here, okay? And then what we can do later with that is we can start to get the mean rate. So regardless of the size of the number of samples here, we're going to do one-tailed matched pairs t-test. We want to be 95% confident that our result hasn't just occurred by chance. We can accept that there's a 5% chance that the results might have just occurred by random error. So we have an alpha value of 0.05, this is our significance value. We have the number of degrees of freedom, which is our sample size minus 1. So I'll just put all of those into the global environment. And then we need to delineate our regions of rejection. So we can get our t critical value by using the quantile t function that we used before. So we can give it the alpha value that we're using here, which is 0.05. We can give it the number of degrees of freedom. We can tell it we want the results in the lower part of the distribution. So the t critical value here is 1.67, 1.68 when rounded. Sorry, we don't want it in the lower part of the distribution, hence it's low equals false, and that's why we get the positive number of standard deviations above the mean. We then need to create the t-distribution curve so we can have a nice plot. So we're going to plot that now. We're going to plot it with our t-critical value shaded in red. So this is the area, our zone of rejection up here, that relates to our significance value. So we can get the d bar value. So this d here, we can subtract the x bar and the x bar 1 and the x bar 2 that we got earlier. So we can get a d bar value up here, 3.39. So that's the d bar, and then down here we just want to get this standard error of the mean of the difference. So to get that, what we need to do is run through this equation. So it's the square root of, and up here we've got the standard deviation of the matched pairs of differences divided by, and then we have the sample size multiplied by the number of degrees of freedom. And when we do that, we end up with basically a t-statistic where we get the d bar divided by the standard error, and we get 11.01 as our t-statistic, so the number of standard deviations above the mean. So it's not even on our chart, it's so high, it's so significant. I mean, so this is a really huge result. So obviously we can quite strongly reject the null hypothesis for our level of significance. So we could be 95% sure in this case that the results haven't just occurred by random. Okay, so we can reject the null hypothesis and accept the hypothesis that the poverty rate has increased over this period. Okay, so it's actually quite a shocking result. Unfortunately, lots of people still living in poverty. So we can then check this by running the p-value, checking the p-value based on the t-statistic that we got. So when we do that, we get 2.81 but to the minus 15. So it's a really, really strong, really significant result. We can test this, so we can use the inbuilt t.test where we feed it the poverty rate for 2010, the poverty rate for 2000. And we can tell it to do a paired t-test at 95% confidence level. And basically it's going to give us a result which is very similar to the p-value that we got, very similar to our t-value that we got as well. So this is basically just supporting the fact that the analysis that we did earlier was correct, and then it's supported by the inbuilt function. So for the non-parametric Wilcoxon matched pairs signed ranks test, we can actually use the same variables we used in the last test, but we're not going to do an inbuilt version of the Wilcoxon matched pairs signed ranks test, which lets us compare the matched pairs from a random sample. Sorry, so I think we are going to use the inbuilt, that's what I mean. So we can use the inbuilt function here by testing the poverty rate for 2010, the poverty rate for 2000. And this produces a a p-value which is highly significant down here. And I think that that's fairly self-explanatory to you. So like the Wilcoxon test, it gives us the test statistic that we don't deal with in this class. Most importantly, it gives us the p-value, which is extremely small. So this indicates that we should reject the null hypothesis. So I think that's fairly straightforward. We've covered that before, that there's a highly significant result here. So look, I just want to go over one more example, and I know it's been a really long lecture and a long lab, and there's been a lot of information to hold on to, but we're just going to basically go over one of those two sample difference of proportions tests that we covered within the book. So if you look at page 165 to 168, then we basically have information on obesity rates within Alabama, and we have that for the year 2000 and the year 2010. So the two sample difference of proportions test lets us compare those independent random sample proportions for their differences. But obviously here what we have are dependent examples. So while this example seems to look like a matched pair sample with looking at year X and year Y, these are independent samples because the same individuals are not sampled at both times. Oh, okay. So that's clear in the book. So in this case, we're looking at the obesity level for Alabama, as I mentioned before, in the year 2000. And what we want to do is we want to actually see if the proportion of the adult population who are actually classified as obese has actually increased significantly over those two time periods. So I think that this is quite nice because we've been able to do it in tandem with the poverty level as well. And unfortunately, obesity is quite highly correlated with obesity levels in, at least in many of the Western countries, in Europe as well. So the obesity level for adults in Alabama increased from 23.9% in 2000 to 32.8% in 2010. So the observed difference of the proportions is actually 8.9%, so it's really quite high. So first what we can do is we can enter the data for 2000. So the number of people sampled was 2,156. So let me just clear this so it's clearer for you. So we've got that first sample size for the year 2000. And then we can do the same by entering the number of people that ranked as obese. So it's 516 out of 2,156. So we basically get a sample proportion of 0.239. So 23.9% of people. And actually we can do the same. I'm not going to run through it in much detail because you know this calculation. We can do the same here, and actually for 2010 we get 32.8%. So it's just backing up our previous examples. We want to be 95% sure that the results don't just occur by chance, so we're going to use an alpha value of 0.05, the significance value. So if our p-value is below this rate, then we know that there's a significant result. Let's enter that into our global environment. And then basically to set up the data for the proportion test, we need a vector for both the x values and a vector for the n values. So we can add those, we can concatenate those values together for x and for n, for those different year periods that we already entered. And actually now we can just use the standard proportion test that's inbuilt into R. So we give it the x values and the n values, and we state the confidence level, and we state all the other parameters that we would like to have. So it's running a two-sample test for equality of proportions. The chi-squared value which we're getting is 62.04. And actually the test statistic is listed as the chi-squared. And as with the one sample version, actually if we take the square root of the chi-squared value, it gives us the z value we would be looking for. So if we just take the square root of this, we actually get a z value of 7.87. So it's incredibly high. We know that at that rate, we're probably going to have a highly significant p-value. So actually when we look at the p-value that we ran before, it was 1.681 to the minus 15, so incredibly significant. So we can see from this particular results that the proportion of Alabama's adult population classified as obese has increased significantly over that time period from 2000 to 2010, which means we're pretty much virtually 100% confident that this is true because there was such a significant, strong finding in our results. Okay, great. Well, I hope that hasn't been overwhelming to you. You've got the lecture now where we've gone over the high-level materials, and then you've got the lab here, which hopefully wasn't too arduous. You've got the code, and you can run this as you feel, as you like at your leisure to understand it. Make sure you read the book. Please read the examples, and don't hesitate to reach out to me if you've got any further questions and if I'm able to help you. So, have a good week. It's been nice to see you again. Thanks for tuning in again to this week's set of materials, and I hope you enjoy the content, and do let me know if you've got any further questions. Thank you. Goodbye.